Thank you very much for taking the time to come to our talk today. My name is Manish Gupta. I'm the Chief Technology Officer at Nikira Labs. We were fortunate enough to receive a DoD Phase 2 program to develop next-generation air monitoring for naval submarines with a special focus on volatile compounds. Nikira Labs is a small, woman-owned business that's located in Mountain View, California. We're actually a micro-business, meaning we have under 5 employees. We really specialize in laser spectrometry and the ability to offer novel optical solutions for DoD applications. We have over 45 years of cumulative experience doing this, building instruments, manufacturing instruments, commercializing instruments. We have actually had some experience starting other companies that have been successful. And our focus here that's unique is, in addition to all this optical expertise, we also want to specialize in sort of rapid, low-cost prototyping and manufacturing techniques, things like 3D printing and laser cutting, that we feel can revolutionize this space and make instruments that are much cheaper, much smaller, and much more portable. We have some experience working with DoD in a previous incarnation, and actually in a previous incarnation we were actually working to transition instruments into the fleet, so we sort of understand some of the process and what's needed to do that. The Navy's key challenge here is that the submarine is a closed environment, which means that when sailors breathe and create other or pollutants, these just stay in the air. So they need to have an active air control system, an atmospheric control system that removes particles by mechanical filters, generates oxygen, and removes CO2 with chemical means, and then removes organic or volatile compounds using, for example, a burner. And this constant system must always be monitored to keep the sailors healthy and safe. And so as we're transitioning into the new fleets, especially the Columbia class, the hope is to develop better monitors and better atmospheric control systems. Currently, the way the Navy monitors these gases is by using something called the CAMS, the Centralized Atmospheric Monitoring System. This is a magnetic sector mass spectrometer that's made by Collins Aerospace, formerly Hamilton Sundstrand. Essentially, it takes gases, it ionizes them, and then sorts them by mass, and that mass is used to determine the compound. It's a proven technology. It's extremely sensitive, and it can measure a whole bunch of things at once. So it's a very strong technology. It's been used by the Navy for many, many, many years. There are a few issues, though, with it. The first is, of course, that it's centralized. That means that the one CAMS unit sits in the middle of the ship, and gases are drawn from all over the boat to this center room. So you have to run tubing all the way down the ship. That's extremely expensive. And also, if there's a hazardous gas, you're then taking that hazardous gas and pulling it through the entire submarine. The other issue is that because you're pulling it down this tubing, anything that's sticky or reactive can't be measured. So, for example, formaldehyde or acrolein or ozone, these sort of new compounds that people are worried about, either stick to walls or they react. So they can't be measured by the CAMS because they don't make it to the central room. Because it's a mass spectrometer, it uses high vacuum, and therefore it's relatively expensive to purchase and maintain and install. So we have this issue now where the cost of maintenance for these units is very, very high. So what the Navy is looking for is alternate and complementary technologies to improve air monitoring in these subs in a variety of ways. Instead of mass spectrometry, Nikira Labs is using a completely new technology called mid-infrared cavity ringdown spectroscopy. In this, you have a widely tunable mid-infrared laser. So it's called an external cavity quantum cascade laser. And you can tune this laser over a large portion of the mid-infrared, for example, from 7.5 to 10.5 microns. And at different wavelengths, different gases absorb light. So you can look at the absorption of those gases to figure out what's in the sample. So, for example, formaldehyde might absorb over here, and water might absorb over here, and carbon dioxide and acrolein, they all have very unique spectrum. The problem is that if you do this normally, just shine a laser across a room, you wouldn't have enough absorption to actually measure, to quantify accurately, because there's just not that much of these compounds. They're trace compounds, and they're very little of each. So what we do is, instead of taking the laser across the room, we put it into two highly reflective mirrors. And it bounces back and forth between these mirrors something like 1,000 times. And we get an effective path length of like 1,000 meters. It's as if we shine the laser across 1,000 meters. And then by using something called cavity ringdown, we shut the laser off, watch the laser decay out of the cell, and that tells us a measure of the absorption and loss in that cell due to these gases. So we can take essentially very, very sensitive absorption spectrum of these gases and then use that to determine concentrations. Here's an example of some of the compounds we've already measured. So for example, the spectrum of formaldehyde is here, ozone, acrolein, and then one of the many refrigerants, R134A. You can see all the spectra look different. It's like different fingerprints. And by fitting these spectra, we use our own sort of proprietary analytics routine. We can actually get the concentration of each one of these compounds separately. So for example, formaldehyde, we have a limited detection of about 0.4 ppm, ozone's around 6 ppb, acrolein is 20 ppb, and so on and so forth. And critically, the system is more sensitive than the permissible exposure limits that is defined by OSHA for almost all of these compounds. And so it's a system that can really meet the sort of needs the Navy has and see all these multiple compounds. This is our first phase 2 prototype. So you can see here all the components that go into an instrument. There's the high finesse optical cavity. There's the external cavity quantum cascade laser. There's some turning mirrors to get it in there. And there's a special highly amplified detector. Then there's the computer, the pump to pull the sample into the cavity, the power supplies, and all the computing that's needed to be done. The reason we backed it like this and made it extractive is because for the first phase 2 deliverable, we wanted to integrate into the existing CAMS rack. In the rack that houses the CAMS, there's an open space, and we wanted to get either fit into that or closely fit into that so that we could integrate it into the same room. We've actually completed all the hardware and electronics fabrication. I'm sorry, when the slide was built, we didn't have the instrument yet. We've already tested it on all the main compounds, and we're actually just testing it on mixtures now, and we intend to deliver it to Navy in this first quarter, and hopefully, if we're lucky, get onto a submarine and do a test deployment to actually monitor some VOCs in an actual submarine environment. So as we noted, the technology has several features that give direct benefits to the Navy. The first is we're using a widely tunable mid-infrared laser. So instead of just looking at one compound, we can look at a whole bunch of compounds and use our analytics to determine the concentration of all those compounds. So in that way, it's similar to a mass spec because you can monitor everything at once. We use this high finesse optical cavity to give a really long path length, which takes our detection limits down to the sort of parts per billion level. One thing I didn't mention earlier is that for the second deliverable, we're actually using an open path. We don't even have a closed cell. We're literally having an open path cavity. And that means we don't draw the sample through any lines, and there's no wetted parts. And so we can measure all these sticky and reactive gases. And we've already shown that we can measure things like acrolein this way. And that allows us to see things that aren't currently seen by the current CAMs. It operates at atmospheric pressure. There's no high vacuum pumps, no leaking issues, nothing like that. So it's a much more robust instrument and has a very low maintenance cost, and you can warm it up immediately. So essentially, it's the time it takes to turn on all the computing, so about a minute. It is a relatively small instrument. It's much, much lower cost than a mass spec, which means, in principle, instead of deploying one in the central unit, you could actually deploy several of these around the sub, and that is actually part of the Navy's future vision of distributed air monitoring systems, or DAMs. And the hope is that you monitor in the actual compartments that matter and don't have to draw your sample all the way through. That also adds to the point that you can actually monitor key components in different compartments. For example, life gases, where the sailors are, and maybe battery outgassing, where the batteries are. Our intention is to eventually transition to the fleet. So we're going to complete this phase 2 effort. There's actually 2 other options with it to make an open path and a test bed. Those efforts are going to include deploying instruments on actual submarines if the Navy permits it. And then we'd like to work with the DoD Prime to integrate the analyzer into the whole submarine atmospheric control system. This is just the monitor. This has to be fed back and increase the burner or change the amount of CO2 that's drawn down or something like that. Right now, our development timeline coincides extremely well with the development of the Columbia-class submarine, which is ongoing. So hopefully, if we're fortunate, we can get onto some of the later submarines. In addition to this Navy application, there are other uses in the DoD. For example, we can also look at gases in hypersonic engine development. So a lot of times when you're developing hypersonics, you have these test stands, and you need to be able to monitor gases in those test stands to compare to your models to help improve the engine performance. And we can do a lot of that monitoring. We can do waste remediation. For example, we've shown that we can do trichloroethylene and tetrachloroethylene, which are actually waste products that have been dumped in the ground. And as DoD and other agencies work to clean up all these things, they need ways of monitoring if there's still stuff coming out of the dirt. We can do a lot of that real-time monitoring. We can also do closed cabin monitoring in other regenerative air systems. So, for example, the space station, or anywhere you have a closed system, like a bunker, where you need to monitor the air and control the air. Ideally, we would serve as an OEM to a DoD prime that's actually developing atmospheric controlling and monitoring systems, someone like a Collins Aerospace. We will require follow-up funding, obviously, to take our prototypes, our phase 2 instruments, and make them into actual OEMs that we can put into these existing infrastructures. And we'd also like to partner with DoD contractors to find other laser-based sensing needs, things like hypersonics. We have a wide suite of laser diagnostics that could benefit DoD. Finally, thank you for listening. I appreciate your time. If you have any questions at all, please feel free to contact me at any time. This is my business card. You can contact me by phone or by email. We'll be very responsive, and hopefully we'll have an opportunity to work together to help the DoD. Thank you. Please note that all content in this talk is either owned or developed by Nikira Labs and cited as shown in this slide. Thank you.